Alright, we're back. Let's continue on to another video. And what we're doing is looking at waveforms in most wind instruments. And if you look at the left column, or no, before we do that, this is a musical instrument, like a pipe organ that has made of a tube, and the tube is opened at both ends. So I'll just, if you look, you see these light blue lines there and there. This represents the tube itself. I'll try and draw that. So we have a tube. And it's open at this end. So this is the one end of the tube. And it's also open at the other end of the tube. This is was kind of confusing the first time I looked at it. The length of the tube is L, so this is the length. And this side will give us air pressure, or variation in air pressure throughout the length of the tube. So points of maximum amplitude, or points of maximum pressure, points of, like here and here, are points of minimum pressure. So this would be compression. If you're familiar with sound waves are made of compressions and rarefactions, as we stated previously. So this is high pressure, compression, and this is rarefaction, low pressure. Again, now we have variation between rarefaction, compression, rarefaction, compression, rarefaction, and then finally down here, R, C, R, C, R, C, R. Now here we have a relatively low incidence of change in pressure per unit length. So this would be a low frequency sound wave. This is a moderate frequency sound wave. And this is a high frequency sound wave. Now this is displacement of sound at various points throughout the length. And again, we still have an open-ended tube, open, open. And this is the point where there's no displacement. That's called a node. And this is the point of maximum displacement. This is an antinode. In order to produce sound in this tube, you need to have an antinode on either end. And this will produce noise or music. We'll do this together. So again, we have an antinode, a node, an antinode. Here is an antinode, node, antinode, node, antinode. So there's no displacement or no movement of air in the column there. And again, antinode, node, antinode. Whoops, I made a mistake. So let's undo that. Antinode, node, antinode, node, antinode, node, and then finally you get the point. Let's go through an exercise. We'll go outside the box. We've identified whether or not there are nodes in it or antinodes. I'll just extend the page and I'll drag this down because we're going to use the same slide. You can rewind if you need to see that again. Let's take a moment and identify how many wavelengths are present. Each of, and this is unusual, I do this different than most people. If we look at this one particularly, you start off, you go through an entire waveform. This one contains a fraction of a waveform. This one contains more than a waveform. I like to identify waveforms and I break them down into parts. I quarter them. So this would be 1/4 of a wave. This is the second quarter of the wave, third, and then fourth. So if we have a complete waveform, we have 4/4 of a wave. In this one, this is the first quarter. This is the second quarter. We have a half of a wave. In this one, we'll just start quartering. we're butchering the waves, if you will. Sorry, this is the first part of the first quarter, second quarter, third quarter, fourth quarter, fifth. You have 6 quarters of a wave. So the wavelength would be a fraction of the total length, and so on. Now, these pictures correspond. This is the air pressure throughout the length. This is the displacement, or how far the wave's moving. In this one, we have 1 quarter and 2 quarters of a wave. So the total number of quarters, 4 quarters of a wave, can't be contained in this tube. 2 quarters of this wave are contained. So the wavelength would be, 2 times the length. Check. Here we have 1, 2, 3, 4 quarters. So the wavelength there would be the length. Here we have 6 quarters of a wave. So the total wavelength is a fraction of that wave. 4/6 of that wave, or 2/3 of the length. Now they're going to give us a formula that we use to find the wavelength. And if my memory serves me, the wavelength, the formula for the wavelength, let's see if we can remember this. It's 2 times the length divided by the number of antinodes. Let's apply this bad boy. So again, lambda is 2L divided by N. We'll see if our dreams come true, if this works. So the wavelength will be 2 times the length divided by the number of antinodes. How many antinodes did we have here? There's 1 antinode in reality that will at either end. So wavelength will be 2L. How many antinodes are here? 1, 2. 2L over N, 2 antinodes, L, and so on. How many antinodes are there? 1, 2, 3 antinodes, 2L over 3, 2/3 of L. And these standing waves in air columns, this is the air, are very similar to the standing waves in strings, in that you have to have, well, you do have nodes and antinodes, and the more antinodes that you have, here 1, here 2, here 3, if you increase the number of antinodes, you'll increase the frequency or the pitch of sound. So let's see what the next question is. And again, there's the formula. Finding the wavelength is 2 times the length over the number of the antinodes, and again the frequency. We're good to go. Let's look at a question. A sound wave resonates in a tube of length 2 meters with 2 open ends. What is the wavelength of the lowest frequency on the tube? That lowest frequency is called the fundamental frequency. I'll try and draw. So I'll draw that tube 2 different ways. Again, if you want to have what's called resonance or sound in this tube, the lowest possible frequency will have a node in the center and an antinode on either end, so we have a point of maximum vibration. Forgive my art. And now my first question is, what is the number of quarters that we have present? Here's 1 quarter, here's 2 quarters. Waves are made of 4 total quarters. So we would need a tube that were twice as long to contain an entire wave. If this tube is 2 meters and we needed a tube that was twice as long, it would be 4 meters. that wavelength will be 2L divided by the number of antinodes. In this case it would be 1. So 2L, or 2 over 1, times 2 meters. 4 meters of tube will do that. So the wavelength will be 2 times the length of the tube. Next, the sound wave resonates in a tube of length 2 meters with 2 open ends. What is the lowest frequency that it will sing at? So the question is, if we have that 2 meter tube, there'll be some frequency. And again, I'll just draw the tube. Sorry for the different color. Here's the waveform. This length of the tube was 2 meters. And we would need that wavelength, as stated previously, is going to be 4 meters. Sorry about that, kind of sloppy. 4 meters. What is the frequency that it will sing at? Since the speed of the wave is going to be 340 meters per second, which is the speed of sound in air, we can calculate this using the wave equation. V is lambda f. F is going to be V over lambda, 340 meters per second divided by 4 meters of tube. So the frequency is going to be about 100 some hertz. 100 some hertz. Would we be able to hear that? Absolutely, because it falls within the audible spectrum between 20 and 20,000 hertz. You can be more specific in your answer. So in air, sound will always travel at 340 meters per second. The speed of sound depends on the medium that it's traveling in. If you have a tube that's 2 meters long, the standing wave that will be produced in that will always have a frequency that is the speed of sound divided by the wavelength, and that tube is going to sing at some 100 some hertz. Actually, 340 divided by 4 is going to be less than 100, but it will still fall in the audible spectrum. Can you predict what would happen if we were to shorten the length of tube? If this wavelength of sound goes down, the frequency will go up. Shorter tubes produce higher musical notes. Longer tubes produce lower musical notes. If we go back to our saxophone picture, let's find that. There it is. Shorter tubes, this is a short tube, produces a high note. Longer tubes produce low notes. So we'll go on through. Now, air columns in closed tubes are going to be a little bit different. Hey, I want to remind you, sound will go down. This is an open end, this is a closed end. Kind of hard to draw. Sound will go all the way down and then bounce and come back. And when sound waves traveling to your left interact with reflected waves, they're going to hit this boundary. Moving to our right, we're going to produce standing waves. Now this slide is different. They put air pressure over here and displacement over here. This is a node, this is an antinode, node, antinode, node, antinode, node, antinode, node, antinode, node, antinode. So as you go in this direction, you're increasing frequency. This is 1/4 of a waveform. This is 3/4 of a waveform. This is 5/4 of a waveform. This is a frequency of 1. This is a frequency that's 3 times greater. This is a frequency that is 5 times greater. So we can look at this. All these tubes are the same length. Length, length, length. You can play different musical notes, different pitches, different frequencies by containing different shaped waves within that length. You can do this with a bugle. A bugle has no keys to change the length of the air column by vibrating your lips with different frequencies. If you have any experience with music, you can produce different musical notes. One thing that you need to realize, that you always had to have a node at that wall and an antinode at the open end. always antinodes on the, let's go back one more slide. Oh, too far. I'm sorry. Sorry about that. There it is. Always antinodes on open ends, open, open, and those are in the center there, are contained within the tube. However, when we have a closed tube on one end, always a node there, and that acts like a fixed boundary which will reflect waves and produce standing waves. So if you look at this, we have a closed tube and it's containing a quarter of the wave. If we look at one complete waveform, the most fundamental frequency will have a wavelength that is 4 times the length of that tube. So that wavelength can be computed by using a different formula, and this is specific for closed end tubes, or excuse me, open and then closed on one end. That is 4L over N. How many antinodes are contained within this first tube? 1. You have an antinode there and a node there. Or actually that's where the node is, and that's the antinode. This is the area of low pressure. This would be an area of high pressure if we go back to the pressure one. And the wavelength is going to be 4 times the L. A sound wave resonates in a tube of 2 meters length with one open end. What is the wavelength of the lowest frequency? If I draw that tube, you'll have a node here and an antinode there, so the waveform will look like that. How many wave quarters are there? 1/4 of a wave. If this is 2 meters long, and 2 meters contains 1/4 of a wave, 8 meters will contain 4/4. Or we can use the formula that wavelength for a tube with one open end is 4 times the length divided by N, the number of antinodes. There are 1 antinodes, and the length is 2 meters, so that will be 8 meters worth of length. Let's move on. A sound wave resonates in that tube, that previous tube. So I'll draw it again. Again, that's 2 meters, and that waveform will look like this. And that wavelength will be 8 meters. What is the frequency that this will sing at? That frequency that it will sing at can be calculated using the wave equation. That was a mistake. It should be V equals lambda F. The frequency is that velocity divided by the wavelength, and that will be 340 meters per second, the speed of sound, because we're in an air column, divided by the wavelength, 8 meters. So you're going to end up with 340 divided by 8 for that frequency, whatever that is. And you can compute that. This tube will also sing at a higher frequency. If this is F, it will sing at a frequency that corresponds with excuse my illustration, a waveform that looks like that. How many waveforms are contained? 1, 2, 3. So this wave in the second illustration will be 3 times as frequent as the top wave. So we'll get resonance or singing at that frequency F. We'll get resonance at 3 times that value for a closed end. And then again 5F, 7F. Can you predict the next one? 9 times the frequency, and so on. Think about this. Why don't you get 2F? Why don't you get 4F, and so on? If I did 2F, let's just go down and draw. If I had a wave that were twice as frequent of this one, it would look something like this. And just imagine this tube and this tube are the same length. Forgive my illustration. If it were twice as frequent as this, we would have 2 quarters contained, and we'd end up with a node, an antinode, and a node. Can you remember what has to be at the end of that tube in order to hear sound? What is that thing called? And what is that thing called? An antinode. And so there's no antinode at the end. Let's move forward and see what we have next. Okay, a sound wave resonates in a tube of length 2 meters within one open end. What is the next resonant frequency? We did this. We said that would be 3F. And again, here's your, let's stick with our colors. Here's your, nah, it's terrible. I'll redraw that. Hey, a little smart thing, if you want to draw straight lines, don't try and do it freehand. Use your line function, and you can draw them like that. Highlight everything, hit Control G to group and dupe, and that looks a lot prettier than I did before. So again, let's get back in gear here. This is the fundamental frequency. The next frequency that it will resonate at will look like that. If this is F, this is 3F, and again 5F, and so on. I'm going to publish a worksheet for you that you can give to kids, and this is a fantastic way of getting used to dealing with what the waveforms in open-ended tubes and closed-ended tubes look like. Again, I'll give that to you, and it's something you can carry on in your work. Alright, let's stop at this point and I'll publish another video.